Assalamu alaikum. Welcome to the second lecture of chapter 6. Chapter 6, remember, is mechanical properties of metals. In the beginning, I will quickly go through lecture 1, so a very brief review of lecture 1, what we did. Then the topics that we will cover today is Poisson's ratio, shear stress, shear strain. Then we will go to describe the tensile test. Then the engineering stress strain diagram that is obtained after the test. And once the stress strain diagram is there, then we will start discussing mechanical properties. And today we will cover modulus of elasticity or Young's modulus and yield strength. So this is today's lecture, inshallah. The topics that we covered in the first lecture of chapter 6 on mechanical properties of metals, we discussed the design, manufacturing and material selection topic with the help of the bicycle frame, different choices of materials that we can have for that. Then we started stress strain in metals, and we started the discussion with elastic and plastic deformation. Then we started talking of engineering stress and strain, engineering stress definition. For an example, another example, then engineering strain, the definition and the units, and then an example about engineering strain. So this was the first part of chapter 6, lecture 1. Now we begin lecture 2. The topic is Poisson's ratio. Poisson's ratio. So don't read below. You know, we have been discussing tensile test and stress strain and so on. In the tensile test, there is a long rod, for example, just like say your pen or pencil, and you hold it in the machine and you pull it, right? You say it is a uniaxial tensile test, you pull it. So it becomes longer, as you have seen in the examples, its length increases. So if it is say a round bar, and if its length increases, what do you think happens to its diameter? Right, your answer is right. The diameter decreases, or the cross-sectional area decreases, right? So length increases, but the diameter decreases. If rather than a round piece, if it was a square piece, a long square piece, right, a long square piece or a long rectangular piece in shape, then again if you are pulling it, its length increases, but now both the width and the thickness change, isn't it? It is not round. If it is round, we can just say that the dia or the radius has decreased. But if it is rectangular in cross section, then both the longer part of that rectangle and the shorter part of that rectangle, they also change in size when the length is changed. So how should we measure the change in dimension in the other two sides? The length is being measured by the machine. When you are pulling it in tension, the force is being measured by the machine, the length is being measured by the machine. So the strain in the direct axial or longitudinal direction, that is directly there. But if we want to find out the change in dimension in the other, for example, if we call it x, y, z directions, then in x direction we know it is the length change, but the change in the y direction and the z direction of the sample we can't. If we want to do it experimentally, it is very, very costly, because we have to have some laser measurement or some infrared measurement which is continuously going, because you see the length is continuously changing, so the other dimensions are also continuously changing. So it will be a very costly setup. Some scientists did it. If you see the name here, Poisson, right? The N is a gunna, Poisson. So this is a French origin name. So the scientist Poisson studied this, and then rather than being forced to do those very costly measurements, he studied different materials and he found a relationship. He found a relationship which is given here, as Poisson's ratio. Poisson's ratio is now the ratio of the strain in the non-axial direction to the axial direction. Longitudinal or axial is your direction, the direction along the length. Lateral means perpendicular to axial or longitudinal. So if this is Z, if longitudinal or axial is Z, then lateral is X also, lateral is Y also. So Poisson's ratio is a number called nu, NU. It is the Roman italic version of N in English, N, the sound of N, but there it is like a slanted V, slanted small V, and it is pronounced as nu, NU, nu. So this is the symbol for Poisson's ratio, and it is the ratio of the lateral strain to the longitudinal strain, which means epsilon x to epsilon z or epsilon y to epsilon z. Why is this minus sign there? Anybody think? Why is there a minus sign in this? Yes, you are right if you have guessed it correctly, because you see, if epsilon z in the longitudinal direction, this is increasing, the length is increasing, right? The length is increasing, but the lateral dimension x or y is decreasing. So therefore there is this minus sign. If there was a plus sign, it would mean that if the length is increased, the dia will also be increased, but that can never happen. You see, if we are pulling the piece, the length is increasing, the dia will decrease. So one increases, the other decreases, therefore there is a minus sign, right? So this is something which is totally new. Now, if you know this is a material property, this is a material property. So if you have a certain steel or an aluminum alloy or whatever, its value will be given to you. So if you know this value and you have found the axial strain, longitudinal strain, then you can find the other one. You see, nu is known, epsilon z is known, so epsilon x can be found or epsilon y can be found. So you see, because of knowing this property of the material, then in the machine where you are doing the tensile testing, you do not have to have a laser or infrared system of a very high cost to find the change in dimension in the lateral side. For an ideal material which does not exist in the world, nu is 0.5. For real materials, it varies from 0.25 to 0.4, the value of nu. And for general metals and so on, it is 0.3, general metals. So you see, if in any problem, if the Poisson's ratio of the material is given, it is okay. If it is not given, you cannot say that Poisson's ratio is not given, so I cannot solve it. You know that you can make this assumption right, that because Poisson's ratio is not given, so I am assuming it to be 0.3 and then solve it. Okay. So this is Poisson's, and let me show you on the figure here. Forget about this one, this will come later on, this one. So you see, there is a piece which is a long piece, and it is a square or rectangular in nature, a square or rectangular. This dashed line is the original size of the material, right? This is the original size of the material, the sample. Now you have applied stresses in the z direction, the axial or the longitudinal direction. So when you apply those loads and it deforms, then it changes in length, right? So the length increases, but if you see, the size on the other side decreases. It was until here, now it has decreased. Here also, the size was until here, it has decreased. So in the x direction and in the y direction, the size has decreased. In the z direction, the size has increased, right? So this will always happen in a tensile test, that if the piece is rectangular or a square in nature, the length will increase, and if the length we are representing as z direction, then the dimensions in the x and y will change. And to find that out, we have defined a new material property known as Poisson's ratio. Its symbol is nu, and it is equal to minus epsilon x upon epsilon z or minus epsilon y upon epsilon z, right? So we are not worried about this one for now, this one. Okay, so this is Poisson's ratio, and it is a huge thing that now without actual measurement you can find the strains in the other two directions. With this, now we have done the normal stress and strain. Remember from your statics course and so on, you have forces in the normal direction, then you have shear forces and you have torsional forces and so on, right? So normal means tensile or compressive, right? That along the axis, right, there is a surface, any surface, and the load is at 90 degrees to the surface, so it is a normal load. If you are pulling it, it is tensile. If you are pressing it, it is compressive. So the previous one which we were defining a stress, a strain and Poisson's ratio. But that was for normal loads. A stress, a strain and Poisson's ratio was for a normal load, and the common example is a tensile example. Now the other type of force application that you know, shear. So don't read again, don't read below. You have done statics. Some of you are already doing solid mechanics also, right? So in statics, you have done the whole course. By the way, let me stop one interesting question. Can you tell me in one sentence, in the course on statics, you did 4, 5, 6, 7, whatever number of chapters. But if you have to tell somebody in one sentence, what is the whole course, the entire course, not each chapter, the entire course of statics is what? Think, pause my lecture, think, and try to come up with a very correct answer, so that when we discuss it, you say, oh yes, my answer was right. Or otherwise, by chance, if it was not right, then you stand corrected, you have finished the whole course. So the whole course statics was what? Okay, it was to find unknown forces and moments, in different types of loading situations. That is it. The whole course, you see, you apply normal loads, tensile or compressive, you apply shear loads, you apply bending moment. In all the cases, can you find the unknown forces in XYZ direction? Can you find the unknown moments in XYZ direction? This is the whole course. That is it. This is the whole course, right? So, you see, this type of a sentence, if you can say, really expresses your understanding of the course. That's now you can define the whole course in one sentence, right? Trying to find out unknown forces and unknown moments in the XYZ direction for different types of loadings. Now, the second question then was that what different types of loadings did you study there, right? So you had tensile load, compressive load, shear load, torsional load, bending. If you see, the whole course is finished, right? Tensile, compressive, shear, bending, torsional. Now, tensile and compressive have one common name. What is it? Yes, you are right. Normal. Shear force and torsional have one common name. What is this? Shear. Right? Shear is shear also, and shear is torsional also. And then bending moment is there, and later on you will see that bending is also a type of normal one.